Greetings. Welcome to today's session. So today we will get started with the next topic, you know, which will be on frequency response analysis. Okay, so we will look at what is meant by frequency response and what are the various concepts associated with it and how it is useful, right? As far as control system design is concerned. Okay, so that's something we will get started off with. So if we recall, as far as our perception or visualization is concerned, we have a plant or a system whose transfer function is T of S. So we provide an input U of S, we get an output Y of S from the system. So we know that Y of S is going to be equal to P of S times U of S, right? So that's something which we know. Now, we have been looking at response of the system to various inputs, right? Step input, impulse input, ramp input, and so on, right? When we are dealing with frequency response, we are going to look at the response of the system to sinusoidal inputs. So what do we do? So we say that let the input U of t be some U naught sine omega t. So we can immediately see that we are considering sinusoidal signal. So this implies that U of S is going to be U naught omega divided by S square plus omega square. Okay, so that's going to be the Laplace transform of U naught sine omega t. Right? So the frequency, the angular frequency of this signal is going to be omega in terms of radians per second, and the magnitude is U naught. Okay, U naught is some positive scale, right? The real number, okay, which indicates the magnitude of the sinusoid. Now, if this is the case, what we do is that, like, we substitute in the equation. So we write Y of S to be equal to P of S multiplied by U naught, right? U naught omega divided by S square plus omega square. Okay, so we essentially get Y of S. All right. So now what we do is that, like, we consider the Planck transfer function to be a ratio of a numerator polynomial and a denominator polynomial, right? Our usual way of representing it. So we are just going to be interested in this discussion on the poles of the transfer function. So let us factorize the denominator into n factors, right? So the root of the denominator polynomial being the poles of the transfer function. Okay. So once again, when we talk about performance, we start off with a stable system, right? I'm sure all of us by now are familiar with that. So we say that we start off with the premise that the plant or system under steady is before stable to begin with. Okay? So we say that let the plant system be bounded input, bounded output stable. And this implies that all n poles, right, lie in the left of complexity. Okay, so this is something which we immediately can understand. All right. So we start with this premise. We are dealing with a stable system. So this implies that Y of S, which we wrote as P of S, sorry, P of S U naught omega divided by S square plus omega square. We can rewrite this as U naught omega multiplied by n of S divided by S squared plus omega squared. We can rewrite it as S plus j omega multiplied by S minus j omega, right? So that's what we do. So we are writing S squared plus omega squared as S plus j omega times S minus j omega, right? So we are factorizing it, okay? And anyway, we are going to have S plus P1 through S plus Pn as the denominator of the transfer function. So that's what we are going to have. So we see that we have n plus 2 first order terms, right, in the denominator of this y of s. Of course, it is understood that some of these will be complex conjugates, right? So that's something which we immediately need to understand, right? So we can observe that, like this is how the expression for y of s will turn out. Now, what do we do if we want to calculate y of t? We essentially take the inverse Laplace transform, right? So, but to do that, we do partial fraction expansion, right? So, how do we do partial fraction expansion? We can essentially rewrite this as C1 divided by S plus j omega plus C2 divided by S minus j omega. So, S plus j omega and S minus j omega, the corresponding residues are C1 and C2. Then we have the n factors, right, associated with the force. So let's call this as A1 plus S plus T1, A1 divided by S plus T1, all the way till AN divided by S plus Tn. Okay, so those are the residues, right, associated with the n poles, right, of the transfer function. So we can see that C1 and C2 are the residues associated with the factors S plus j omega and S minus j omega, and A1 through A1 are the residues associated with the first order terms associated with the n pole. Okay, so in summary, what we have done is that I'm just going one step before. So this implies that y of s, which is nothing but P of s multiplying u naught omega divided by s square plus omega square. Okay, that's going to be equal to, right? And let's write this in a different way. 1 minute, sorry. The denominator, what I'm going to do is that, like, I'm just going to write it as s plus j omega multiplied by s minus j omega, right? Because s square plus omega squared, we factorize as s plus j omega times s minus j omega. That's going to be equal to C1 s plus j omega plus C2 divided by s minus j omega, right? Plus A1 divided by s plus T1 all the way till AN divided by s plus Tn. Okay, so these are the n plus 2 terms, right? Okay. So now, if we look at this partial fraction expansion and we take the inverse Laplace transform, what is going to happen? Let's do that. Okay, so we will see why this thing becomes important, right? So let's say take the inverse Laplace transform. What will happen? We will have an expression for y of t, right? So taking the inverse Laplace transform, we will have y of t to be equal to C1 e power minus j omega t, right? Why? Because as we all know, the Laplace of e power minus at is going to be equal to 1 by s plus a, right? So that is the Laplace transform of e power minus a. So the Laplace transform of e power minus at is 1 divided by s plus a. So consequently, if we take the inverse Laplace transform of 1 divided by s plus j omega, we get e power minus j omega t, right? So that's what we get. And then we will have plus C2 e power j omega t plus A1 e power minus T1 t all the way till AN e power minus Tn, right? So this is what we get, okay, if we take the inverse Laplace transform. Okay, so we can make a very interesting observation, right? So what do you think will happen to all these terms, okay, involving e power minus T1t to e power minus Tnt as t tends to 0, sorry, t tends to infinity? They tend to, so please note that all n poles lie in the left of complex plane. So what can you say about e power minus t1t to e power minus tnt? So if any pole lies in the left of complex plane, its real part is negative, right? Is it not? Right? So what can you say about e power minus t1t when the real part is negative? It will go to 0, right? So all these terms would tend to 0 as t tends to infinity. Okay, so that is the result. So consequently, we get something very interesting, right? We universally see that as limit t tends to infinity. What is the y of t, value of y of t? We will see that it's going to be equal to c1 e power minus j omega t plus c2 e power j omega t. Okay, so this is what we call as a steady state output, right? I hope the reasoning is clear, right? So as to how we got the steady state output, which is essentially the limit t tending to infinity y of t to be c1 e power minus j omega t plus c2 e power j omega t. Okay, so because the terms involving the n poles would tend to 0 as t tends to infinity because the poles are all in the left of complex plane, right? So that is the idea. All right. So now the question becomes, how do we get C1 and C2, right? Because that is still left behind, right? So how do we get C1 and C2? So how do you think we can get C1?
Maybe by given boundary conditions.
You recall how we did partial fraction expansion? See, C1 is the residue associated with s plus 1 by s plus j omega, right? So what do we do when we want to find the residue? We multiply by that factor and substitute the root, correct? Is it not? Right? So we first multiply both sides by s plus j omega. Then what do we have? We have p of s u naught omega. If we multiply by s plus j omega, we will be left with only s minus j omega in the denominator. Then that will be equal to C1 plus C2 s plus j omega divided by s minus j omega plus A1 s plus j omega divided by s plus C1. Okay, all the way till an s plus j omega divided by s plus C. I hope all of you agree with that, right? So, correct. So this is the usual way of doing the partial fraction expansion, right? Is it wrong? Now, what do we do if you want to find C1 after multiplying by s plus j omega? What is the root of s plus j omega? We substitute s equals minus j omega, right? Correct. So if we substitute s equals minus j omega, all the terms other than C1 on the right hand side will vanish, right? So if I substitute s equals minus j omega, I will get c of minus j omega, u naught omega, and what will happen to the denominator, s minus j omega? I will get minus 2j omega, right? Do you agree? And that will be equal to C1. Okay, so please stop me if there are any questions. Okay, all right. Okay, so please note that we can we want to find out the residue C1. In order to find the residue C1, we just multiply both sides by s plus j omega and substitute s equals minus j omega. Now, I'm just taking a slight detour. If you look at the complex function, right, p of j omega. See, p of j omega is going to be a complex valued function, right? Is it not? So we can write p of j omega in terms of its real part and imaginary part, we can also write it in terms of its magnitude and phase, where we can essentially write P of j omega as magnitude of P of j omega e power j phi, where phi is the phase of P of j omega. Right? So this is another representation, right, of the complex quantity P of j omega. Right? So as we already know, any complex variable we can write in terms of its real part plus j times the imaginary component, right? We could also write it in this format. That is like we can have the magnitude multiplying e power j phi, okay, where phi is the phase. Then we can immediately see that P of minus j omega, okay, will be equal to, wherever we had j omega, we just substitute minus j omega. So that will become P, the magnitude of P of minus j omega and e power minus j phi. Okay, so whereas we add a negative sign because the phase of P of minus j omega will be the negative of phase of P of j omega. And the magnitude of P of j omega and the magnitude of P of minus j omega are the same. Okay, the magnitude is not going to change because we add that negative sign. Okay, so P of minus j omega is going to be the magnitude of P of j omega times e power minus j phi. Okay, please note what the quantity P of j omega is. P of j omega is what is called as a sinusoidal transfer. Okay, so this is a specific name. Okay, when you substitute S equals j omega. So when we substitute S equals j omega, the quantity that we get, okay, is going to be a complex valued function, and that is going to be what is called as a sinusoidal transfer. So we are going to express P of minus j omega in terms of its magnitude and phase. So this implies that C1 will be equal to P of minus j omega, which can be written as P of j omega magnitude e power minus j phi u naught divided by minus 2j. Why did I write like this? Of course, this omega and omega cancel off, right? So that's all we get. Okay, so this is the expression for C1. All right, this is C1. So similarly, we can get C2, right? So C2, what do? We multiply both sides by S minus j omega. So what do you think will happen? This will result in P of S u naught omega divided by S plus j omega now in the denominator. That will be equal to C1 S minus j omega divided by S plus j omega, then plus C2, right? Then A1 S minus j omega divided by S plus P1 all the way till AN S minus j omega divided by S plus P1. Okay, so that's what we have. So then what we have is that, like, we essentially substitute S equals j omega. Okay, so the root of S minus j omega is going to be S equals j omega. So what happens? You will get P of j omega u naught omega divided by 2j omega, right? That's going to be equal to C2. So this implies that C2 is going to be, this omega will get cancelled off, right? So what will we have for C2? P of j omega is going to be the magnitude of P of j omega e power j phi, right? And then u naught divided by 2j, correct? So that's what we will have. All right. Okay. What to say? Clear? Till now, right? So any questions till now? Okay. So if not, we will go on, right? So we will see what is the end result of this derivation shortly. Okay, we will interpret it physically also. Okay, so that because that's something which is very important. Okay, so what we will also learn what is the physical interpretation. So having done this, now let's go back to the steady state output. What was the steady state output? Steady state output was nothing but the limit t tending to infinity y of t which is going to be equal to c1 e power what did we get? We got 60 minus j omega t. Then if you recall, this was the steady state. Okay? So this was derived as a steady state. Okay, I'm just writing it. Now what I'm going to do is like I'm going to substitute for C1 and C2. Okay, so that's all I'm going to do. So if we substitute for C1 and C2, what do we get? So this implies that the steady state output is going to be equal to limit t tending to infinity y of t. We are going to have, if I substitute for C1, C1 is going to be equal to magnitude of U naught, okay, minus U naught divided by 2j, right? I can write like this, right? So minus U naught divided by 2j, magnitude of P of j omega e power minus j phi e power minus j omega t, right? So that's what I will have, okay? Then what will be C2? I will have plus U naught divided by 2j, magnitude of P of j omega e power j phi e power j omega t. Okay, so I hope it's clear, right? I just substituted what that's it. I have not done anything more. Now, what do you think is e power minus j phi times e power minus j omega t? So please note that e power a times e power b is going to be e power a plus b, right? All of us know about that, right? So consequently, e power minus j phi times e power minus j omega t, I can rewrite as e power minus j of omega t plus phi, right? I hope I can rewrite it this way, right? Similarly, e power j phi times e power j omega t will be e power j times omega t, correct? So I hope this simplification is clear to all of us. All right. So once again, please stop me whenever there is a question. Okay. So I hope that this is clear. Now going ahead, so this will give us. You can immediately see that U naught magnitude of P of j omega is now common. So if I take that out, I will have e power j omega t plus phi minus e power minus j omega t plus phi, right, divided by 2j. Okay, so that's what I have, right? So if I take the term u naught magnitude of p of j omega as common, right? So this is what you have. Now, what is this? So can you recall what are meant by Euler's relation in complex variables? So if we recall what are called as Euler's relation, so we will see that e power j theta is going to be equal to cos theta plus j sin theta, right? So that is one, and e power minus j theta is going to be cos theta minus j sin theta, right? So consequently, one can rewrite cos theta to be equal to e power j theta plus e power minus j theta by 2, and sin theta to be equal to e power j theta minus e power minus j theta divided by 2j. Okay, so that is the other relationship. Okay, so these are what are called Euler's relation. Okay, some complex algebra. So now, if I use the Euler's relations here, what will we get? What do you think we will be getting if we use the Euler's relations here? What will be the term in the square bracket?
Sin omega t plus phi.
Very good. It will be sine of omega t plus phi. Okay, so this will imply that steady state output is the limit t tending to infinity y of t is going to be equal to u naught p of j omega magnitude sine of omega t plus phi. Okay, where phi is nothing but the phase of p of j. So that's very important. Phi is nothing but the phase of p of j. All right. Okay. So this is a very important result. Okay. So I just wanted to spend the time deriving this expression because of the physical value or the practical value. Okay. This particular concept carries. Okay. We will be discussing this, and we will also apply it to practical problems to learn. Like how this becomes very important. So let's look at this, right, from a very broad perspective. Okay, so if I draw this block diagram, okay, I have my plant or the system. So what we do is that, like, we are providing an input u naught sine omega t, right? And I'm sure all of us agree to that. Now, if I provide this to the plant, of course, I'm assuming a stable plant. Okay, to begin with, a stable system. If I wait long enough, right, if I allow my output to settle down, what will happen is that the steady state output is also a sinusoid of the same frequency omega, okay? And it is scaled in magnitude by the magnitude of p of j omega and shifted in phase by the phase of p of j omega, okay? So that is the important result, okay, that we can get out of this particular discussion. Okay, so what is the important note that we can so it can be inferred that the steady state output of a stable LPI dynamic system, causal dynamic system, okay, in a response to a sinusoidal input, okay, is also a sinusoid. I'm writing this in caps, sinusoid of the same frequency as that of the input. Okay, so this is a very important result. Frequency as that of the input. Okay, but scaled in magnitude by the magnitude of P of j omega, which we call as a sinusoidal transfer function, and shifted in phase, right? The phase of P of j. Okay, so this is a property that is an important characteristic of stable linear time invariant system. Okay, so and we will discuss why it is important. Okay, so this is the important result. Okay, from this discussion. So once again, let me repeat this. So we have a stable linear time invariant system to begin with. We provide a sinusoidal input of the form u0 sine omega t. Then what happens is that like we wait long enough and then like we look at the steady state output. What happens is that the steady state output is also the same frequency as that of the input. Okay, so that is very, very important. But the magnitude of the input u0 is scaled by the magnitude of the sinusoidal transfer function P of j omega, and the phase of the sinusoidal input is shifted by the phase of the sinusoidal transfer function P of j omega. Okay, so that is what we have. Okay, so this is extremely important, right? Why? Because of multiple reasons. So the first reason is that suppose if we are given a system, right? We take some problem related to your day-to-day activity, right? So we want to apply whatever concepts we learn in this course, right, to the system. Now, first we need to ascertain whether the system under study can be approximated as an LTA approximation, right? So then, how do I ascertain that? So what we can do is that like one way of checking whether a LTA approximation is reasonable for the system under study is to give the system a bunch of sinusoidal inputs of different frequencies and check the outputs. Okay, if the outputs coming from the system are also sinusoids of the same frequency as that of the input sinusoid, then we know that the system is going to be can be reasonably approximated as a linear time invariant system. Okay, so that is the main let's say conclusion, right? So that we can draw, all right, from this particular exercise. Okay, so that is one important aspect. Another important aspect is that this concept can be used to experimentally determine the transfer function. Okay, so the frequency response is a useful tool. Okay, we are going to do this exercise as we go along in the project. So we will see that the frequency response is a useful tool to experimentally determine the transfer function of the system. So what do I mean by that? Let us say I conduct a lot of experiments, okay, using various frequencies. Okay, what I can do is that like I can get the magnitude of P of j omega by dividing the magnitude of the steady state output and the magnitude of the input. Okay, so this is one measure I can get from the experiment, and I can also get the phase of P of j omega by subtracting the phase of the steady state output and the input. Okay, so if I'm able to do this right from experiment, I can get P of j omega, right? So if I get P of j omega, I get the Planck transfer function. Right? So, so in a certain sense, you know, like I essentially can determine the Planck transfer function using experiment, okay, by applying sinusoid of varying frequency. All right, so that is something which is very, very important. Okay, so essentially, this P of j omega is what is called as a sinusoidal transfer function. So how do we represent it? So if I were to take an example, let's say we take a simple example, we take P of s to be 1 by x plus 1. What happens is that like P of j omega will be equal to 1 divided by j omega plus 1. Okay, so we could find out the magnitude and phase from here itself. Okay, so if you have magnitude or what to say, a ratio of complex function, the magnitude of that ratio is going to be the ratio of the individual magnitude, and the what to say, the phase of the transfer function is going to be the phase algebraic sum of the individual phase. So what do I mean by this? So if I have this to be p of j omega plus 1, of course, let's do the traditional way, is to multiply by the complement, right? Conjugate, right? 1 plus j omega, so conjugate is complex conjugate is 1 minus j omega. Then what we get? We get 1 divided by 1 plus omega square minus j omega divided by 1 plus omega square, right? So, so this is the real part of p of j omega. And we have the imaginary part of the function p of j. Of course, one way to get the magnitude and phase is to essentially square the real part, square the imaginary part, add the sum, and then take the square root. As we just discussed, we can also get the magnitude of this particular term, right? 1 divided by j omega plus 1 or 1 plus j omega is going to be equal to the magnitude of the individual factors. So magnitude of 1 and 1 plus j omega. Magnitude of 1 is going to be 1. The magnitude of 1 plus j omega, as we know, is going to be 1 plus square root of 1 plus omega square, right? So that's it, right? So it's pretty simple to get this. This is the magnitude of p of j omega in this particular case, right? So this is the magnitude of p of j omega in this particular example, right? So similarly, the phase of p of j omega is nothing but the phase of 1 by j omega plus 1. Once again, this can be expressed as the phase of 1 minus the phase of j omega plus 1. See, the phase of 1 is 0. The phase of j omega plus 1 is going to be tan inverse omega, because in general, the phase of any complex variable is going to be tan inverse of imaginary component by real component, right? So we're going to get minus tan inverse. So the answer will be minus tan inverse omega. All right, so this is what we will have. So consequently, we are going to have this. As from this example, it is clear that the magnitude of 1 by 1 plus j omega is 1 divided by square root of 1 plus omega square, and the phase of 1 divided by 1 plus j omega is going to be minus tan inverse of omega, right? So now the question that we ask, so we can immediately observe that the p of j omega depends on omega, right? How do we represent or visualize this sinusoidal transfer function? Okay, p of j. Okay, so that is a very important question, right? So because as we can immediately observe, p of j omega varies with omega. So we are going to learn two important tools. Okay, the first one is what is called as the Bode plot. Okay, so in the Bode plot, what we do is that, like, we plot the magnitude of p of j omega. This is omega. Okay, and the phase of p of j omega, this is omega. Okay, as two separate plots. Okay, so this is what is called as the magnitude plot. Okay, and this is what is called as the phase plot or the angle plot. Okay, so the Bode plot will have two subplots. Okay, so a subfigure, wherein in one subfigure we essentially plot, like the magnitude of p of j omega versus omega and the phase of p of j omega versus omega, right? So those will be the two subplots involved in the Bode plot. The second one is what is called as the Nyquist plot. So in the Nyquist plot, what we do is that, like, we plot the real part of p of j omega. This is the imaginary part of p of j omega as omega is varied. Okay, so that's what we have. Okay, we do this in what is called as a P of S plane. Okay, so what is this P of S plane? Essentially what we do is that this is once again a complex plane where we essentially plot the real part and the imaginary part. But only thing is that like we are plotting the real part of P of j omega and the imaginary part of P of j omega, right? As omega is varying from between the range of values of, right? So essentially that is the Nyquist plot. Okay. So we'll see that by and large we are going to use the Bode plot in our design, but we will look at both of these plots. We will essentially look at Bode plot to a large extent. Okay, but we will also quickly look at what is the Nyquist plot, right? So that we are aware of it. So we are going to learn about the Bode plot in greater detail going forward. Okay. So any questions on what we have discussed in this lecture? So yeah. So if not, let me stop this lecture here and then we'll continue in the next.